this subject. So I'm going to talk about Young-Baxter equation, which is a well-known thing, and the means to solve this equation are very well developed. But I'd like to describe some alternative approach to it, just motivated by the fact that knowing different approaches may reveal some new features. So the outline is the following, so 5 items I'm going to address. Rigid R-Matrices, I'm going to precise this property called rigid because it is this property which is most important for construction of not invariants. Then I'll recall how the standard approach to construct R-matrices from Hopf algebras, and then I'll give an alternative approach through Braided Hopf algebras. So luckily Anna yesterday gave a nice introduction to Braided Hopf algebras, so I will just recall important difference compared to usual Hopf algebras. And then I will turn to the subject of my talk, which is a structure of Braided Hopf algebras on exterior algebras. And I should point out that these are just usual exterior algebras, not Q-deformed. And I will finish with further questions. So, rigid R-matrix, what is it? So, first, R-matrix is just a vector space with an invertible linear map from tensor square of this vector space to itself, which satisfies this homogeneous of order 3 algebraic equation. So I use unusual notation, prime and double prime, to indicate how R is put into tensor cube of the vector space. And rigidity comes is related first to finite dimensionality of the space, and the most convenient way to explain it is to choose a base. Although the definition does not depend on the choice of base. So let us choose a base in V, denoted by this B. Then we have a canonical dual basis in the dual space. And then we, for any linear map F from V squared to V squared, we define its partial transpose, which mixes up the dual space and the initial space. Which is defined by this explicit formula in terms of basis elements, or more conveniently, it is better visualizable graphically if we think of F as a box with 2 incoming legs and 2 outcoming legs, and then we turn.
But you put them in a funny order. You put them in a funny order. Those legs.
Why?
Because V.
No, initially F is just V. Probably it's worth of drawing first F. V. And then F tilde is here, where I turn.
Okay.
Yes, let me draw it here. F tilde then becomes like this.
Okay.
Yeah. And this I try to draw here, and by color I distinguish between dual space and the space itself. So the rigidity condition means that this partially transposed matrix and its inverse are invertible as the linear maps. And I claim that given a rigid R-matrix, there is an algorithmic way to produce a low not invariant, actually, with values in the endomorphism algebra of the vector space V. And to be concrete, here is an example of.
So but you don't have condition, so the inverse will be the same somehow. If you invert and then do the tilde, it's the same as doing the tilde and then inverting?
Not at all. Not at all. They do not commute these operations.
Okay.
But it is true that sometimes it may happen that, for example, the inverse of f tilde, of r tilde, is the inverse of r, for example. But usually it is not the case. Okay, so here is an example I like.
Mutually inverse.
Sorry?
So r tilde, r minus 1 tilde.
Should be invertible.
It's equal to identity. So if I compose.
No, not at all. No. And even more, I don't think that they are composable. Because they act from different vector spaces. Yes, okay, so here is an example which I will use subsequently. So this is why I give it right here. But so why I give it here? Because it is simple. So you see the R-matrix, so it is denoted tau p. So this is a solution of Yang-Baxter equation in this sense. So the notation is such that theta is just a helicide theta symbol, which is 1 if the left argument is strictly greater than the right argument, and 0 otherwise. And the NP, for some reason, I use instead of Q, because when you compare to standard constructions, P happens to be Q squared. So this is why I distinguish.
Any relation with the Bural representation? It looks like the same coefficients.
So this is rigid when dimension of V is finite, and if you plug into this construction which I mentioned, the outcome will be Homological polynomial specified to SLN. Now, let me just recall you what is the standard. What is the standard approach to construction of R-matrices? So the input is a Hopf algebra with invertible antipode. Then there is an algorithmic procedure which consists of constructing another Hopf algebra, which is called quantum double. Then you study its representation theory, namely the finite dimensional representation theory. You pick such representation. Then, so the quantum double comes equipped with a universal R-matrix. You evaluate this universal R-matrix at this representation, and the result is a rigid R-matrix. And I'd like to repeat here that the input can be any Hopf algebra with invertible antipode. So there are no restrictions whatsoever. No reason to stay with quantum groups, for example. But to be concrete, here is the example. We pick the Borel algebra of UQSL2, which is given by this presentation. Then you continue this algorithmic part. So you get a quantum double. Which is close to UQSL2, but a little bit bigger because the carton gets doubled. You study representation theory, and for each integer there is a one irreducible representation. You evaluate the universal matrix for such representation, and the outcome is a rigid matrix, which leads to n-colored Jones polynomial. And now, here is a new approach. So it is based on Braided Hopf algebra. So that's the reason. So I recall you what is the Braided Hopf algebra and what is the difference between the usual Hopf algebra. So we take So what is a braided vector space? Braided vector space is just a vector space with an R matrix defined over it, which I just described previously. And then braided Hopf algebra is a braided vector space with five linear maps called product, co-product, unit, co-unit, antipode. Just exactly the same type of maps as in the usual case. But the only difference is that the so-called braided, the compatibility condition, which contains the symmetry in the usual approach, get replaced by the braiding in the.
And this tau is the same as R?
Which is denoted tau here. Just to, because there will be another R, which is denoted rho, but
it's not a permutation.
It's permutation if you are in the usual context of vector spaces, but otherwise not. Even it doesn't square to identity. And here is a graphical description. Actually, this slide contains the full set of all properties of a braided Hopf algebra. So this is braiding, which replaces the permutation. This is the product. The convention here is the same as the convention for Anna. Everything you should read from bottom to top. I mean the input in the bottom, output in the top. So the product, so you see you have two inputs and one output. The product is the one input, two outputs, unit, co-unit, antipode. And here is the property. So the associativity of the product, unitality of the unit, and the end product, or associativity, co-unitality. So these two axioms just symmetric with respect to graphical reflection. So they are dual notions. Then this is the invertibility for the antipode. And this is the compatibility, something we've seen in the talk of Anna yesterday. And here is extra properties which we see already the braiding here, but it should satisfy also, I mean, all morphisms, structural morphisms should be compatible with braiding, in the sense that, for example, the unit should pass freely through the braiding from both sides, likewise for the co-unit, for the antipode, and also for the product. You see the product passes through the braiding, but you should take into account that the product carries multiple legs, so you should treat the braiding accordingly. From the sides, likewise for the co-product. And one important thing, usually we take the symmetry for granted because it is just permutation or super permutation in the super case. But in the braided case, often braiding can be very complicated. And this formula, which is the equivalent form of the compatibility relation, allows us to express the braiding entirely in terms of structural maps of the Hopf algebra. As you see here, you have 3 copies of the product, here, here, and here, 3 copies of the co-product, and 2 copies of the antipode. And the result is the braiding. So if you don't know how the braiding looks like explicitly, but you know that your object is a braided Hopf algebra, then you just calculate the braiding through this formula. And you can derive some properties which are very similar to the properties we know for usual Hopf algebras. For example, this property which relates the antipode of the product of 2 elements to the product of antipodes of factors which you multiply. But usually here we use just the permutation, but this time you should use the braiding in order to be consistent with the properties of the Hopf algebra. Now, the natural question: how can we find the braided Hopf algebras? And then the example below shows how we can proceed. We just take braided vector space. I mean, recall that it is just a solution of Yang-Baxter equation over some vector space. And then the tensor algebra of this vector space is canonically braided Hopf algebra. But you should be careful. You should induce from the input braiding for the vector space V, the braiding for the tensor algebra. So it means that you have to use what physicists call a fusion as many times as the number of factors in the tensor algebra. And more interestingly, so we know that tensor algebra is too big algebra, just free algebra on say, a chosen basis of V. Usually it is more interesting to reduce it by imposing some relations. And there is a canonical way of doing this in a maximal way, in the sense that this is, you cannot reduce it any further to stay with the Hopf algebra. And this is called Nichols algebra, which is the quotient of the tensor algebra by a certain ideal, which is a maximal ideal containing all primitive elements of degree bigger than 2. I forgot to say that so the Hopf algebra structure in the tensor algebra is fixed by declaring all elements of V, of the input vector space, to be primitive. Primitive means this. And as a remark, so the primitive element is the next in complexity after group-like elements. But in any tensor algebra or any Nichols algebra, there is only one group-like element, the unit element. There are no other group-like elements, but there are many primitive elements, in particular the whole input vector space. But in the tensor algebra, in general, there could be primitive elements of high degree. And the Nichols algebra is exactly the case when you declare all these high degree primitive elements to be zero.
How an element of degree 2 looks like?
Sorry?
How a primitive element of degree 2?
Commutator?
Some linear combination of products of generating elements.
No, but the vector space is fixed and all the other structure is irrelevant, so you should be able to just say it.
It's a Freely algebra.
The Freely algebra.
It's a free algebra, yeah. But so you should combine the same degree elements somehow, and in such combination you can obtain primitive
You
elements.
cannot write.
But like, is it like x times y minus y times x?
Yeah, let me be more precise. Let us take V to be T, V to be C x, and T of V is just the polynomial algebra in X. And then let tau be, actually this is my example on the next transparency. Okay, but look at the example. So that's what I'm going. So you just put tau x is q x tau x, but let us take q equal -1. Then x squared is primitive.
Oh, so it's xy minus yx if the braiding is trivial.
It's primitive because you have to be careful. You should use the compatibility condition in the for calculation of the coproduct of x squared. Namely, x squared delta is x tensor 1 plus 1 tensor x, times x tensor 1 plus 1 tensor x. And then you start to distribute. So this times this, so 1 passes through x, no problem. So it's x squared tensor 1. Likewise, this times this primitive part of this coproduct. But non-primitive part comes from here times here, but 1 gets permuted with 1, no problem. It gives x tensor x. But the last term here, so you x meets x. So you use a braiding, which produces minus 1. And then they get multiplied by 1 from two sides. So you get minus x tensor x. So this cancel out, you get a primitive element. But more generally, you keep Q generic, and then there are no high degree primitive elements. So the Nichols algebra coincides with the tensor algebra in this one-dimensional case. But my message here is that we construct R-matrices from Braided Hopf algebras by adding an automorphism of the Braided Hopf algebra. And in a sense, automorphisms replace the representations in the traditional approach. And how it works? Here is the formula. We don't need any doubling, just explicit formula for the R-matrix. As you see here, it's graphical form. So phi is automorphism. The only thing is lambda r. It's a right action of the algebra on itself through this action, which looks like adjoint action, but it contains also the automorphism. So if you choose identity automorphism, this is just the braided version of the adjoint action. But for me, the presence of the automorphism is crucial. And just take the polynomial algebra with this braiding, and then we take automorphism like this. So the multiplication of the generating element by negative integer power of q, and then it happens that this vector subspace, n plus 1 dimensional vector subspace of the polynomial algebra, stays invariant under this linear map rho. So it produces a finite dimensional sub R-matrix. And it is rigid. I didn't mention it, but rigidity comes just from the invertibility of the antipode. So you plug and you get n plus 1 colored Jones polynomial. No SL2Q, SL2, nothing like this, just polynomial algebra, and one parameter which controls the braiding.
So I have a question.
Yeah.
Is there an overall, not theoretic or diagrammatic interpretation? Namely, if I give you a long knot,
yes,
and you want to evaluate it in this using this algebra, can you transform it to some other knot or tangle or messy diagram and then evaluate it using your input algebra?
As far as I know, no. At least I don't know if this can be used. But keep in mind that the algebra is infinite dimensional, so literally you cannot work on the algebra level. You have to cut out a finite dimensional subspace where the R-matrix acts invariantly. And then you use just the usual Rishtikin-Turaev functor, but adapted to long knots. And this is why I'm saying that the automorphism plays the role of the representation. So you, by varying the choice of this exponent, you vary the dimension, and so that's how it goes. Okay. But of course, if your algebra is finite dimensional, then no need for specifying subspaces. You can take a most generic automorphism, and it will immediately produce on the algebraic level. Okay, now I am turning to the subject of my talk. So the exterior algebras. So here is the first theorem. Here you recognize the R-matrix which underlies the complexity polynomial. But this time we use it as an input braided vector space. And then the theorem is the following. So the Nichols algebra associated to this braided vector space as an algebra is just the exterior algebra without any deformation. But of course, there is a parameter p, so something gets deformed. And first, it is contained in the braiding, and second, in the coproduct, as we will see in a moment. But just to keep in mind that we are dealing with a braided Hopf algebra, so I use a slightly modified notation for the exterior algebra by adding the subindex p.
So your V is always finite dimensional or arbitrary?
This is always, if V is finite dimensional, yes, but V is not obliged to be finite dimensional.
Arbitrary.
Then B of V is not finite dimensional. But otherwise, if dimension of V is n, dimension of BV is 2 power n. And here is a set theoretic basis for the exterior algebra, which is you know very well, but I make it more explicitly set theoretical. So we have an ordered basis. I forgot to mention that the basis should be linearly ordered. And so this B choose K denotes just the all size K subsets of this basis set. And P fun B is just the subset of finite dimensional finite subsets of B, because B for me might be infinite set. And then set theoretical basis just is labeled by finite subsets of the basis. And if we order them in a canonical way in the increasing order, then the basis element is given by just their product. We are in the exterior algebra, we take their product. But if you start exchanging, of course, you get the extra signs. And then let us extend the Heaviside function to subsets just by summing over corresponding elements. And this is gamma k just serves to denote this quadratic exponential in p and this times sign in front. And then we have the product formula, which is just the product in the exterior algebra. But so the sign is controlled by the parity of this set theoretical version of Heaviside. And most importantly, coproduct. We have explicit formula for the coproduct, and as you see, it is deformed by presence of P. But otherwise, it is pretty simple, because if you go back to non-deformed case, which corresponds to P equal 1, then essentially coproduct becomes a product, but in dualized form. So you see, it is a very nice formula. I like it very much myself, because it's difficult to imagine anything simpler than that. A very mild deformation. And so antipode acts diagonally by multiplication with this coefficient gamma, which is defined here. So it sees only the degree or size of the set, but not interior composition in terms of individual elements. And now here comes the Moy calculus. So Louis Adrien should be interested from that moment. So so the integers, in Moy calculus, we put some integers on the oriented edges. And what are these integers? These are just set sizes with respect to this natural grading in the exterior algebra. Saying differently, these are homogeneous elements of fixed degree. And then, as I said, usually it is difficult to describe in explicit terms the braiding because our input braiding was already not very simple. And but using Moy calculus, you can write to some extent the explicit formula if you accept the Moy diagrams. And actually, the analog of this formula was known already from the work of Murakami Osuki Yamada, who produced this Moy calculus by the initials back in 1998, and followed by the work of Kautis, Kannitzer, Morrison in 2014, where they re-derived the analog of this formula. But the important point here that we prove it using the Hopf algebra structure, namely by expressing the braiding in terms of structural constants. And as you have seen, the structural constants are quite simple compared to complicated braiding obtained by fusing all these multiple edges. Yes.
Usually in a situation with a braiding, I would expect that if you replace the braiding with the inverse braiding, you would retain all the structural properties. Is this true of braided Hopf algebras as well?
I see, but here we don't never use actually the inverse braiding.
Okay.
Somehow it is some problem even.
Yeah. So I'm surprised that this formula on the right picks out this braiding and not the inverse.
Yeah.
Okay.
So you can invert the braiding at cost of all the structural morphisms.
They would change. Okay. Great. Thanks.
Yeah, and Louis Adrien, you can point out that in existence formulas, you have here something different, right? Even depending on multiple coefficients, I guess, in usual Moy calculus. So, so the message of this talk also is the fact that the Moy calculus can be realized in different ways, retaining the same diagrammatics. Okay, now, but we can go further here. We can explicitly calculate the matrix coefficients of the grid. And this transparency just explains how we do this. So we remember that the basis elements are indexed by subsets of the set of basis elements. And here I use a Venn diagram, Venn diagram, where we put set E, set F, the intersection, and some complementary sets, which I hope clear from the picture. And using all these associated sets, we define a scalar, which is explicitly given in terms of this set theoretical Heaviside theta, which enters in the power of p, also the power of -1, and most importantly, some product which is some power of p -1. Still, the exponent is expressed in terms of Heaviside theta. And an important point to remark is that so this coefficient doesn't vanish, which means that no factors become 0, if and only if the size of subset H is at least as big as the size of G. And this map from G to positive integer, to non-negative integers should be first get into strictly positive integers, and it should be injective. In this case, this beta does not vanish. And the theorem is the following: so the the grading in the algebra acts on these basis elements according to this formula, where the coefficient is given by this beta coefficient. So we have an explicit factorized formula for the matrix coefficients. And the summation runs only over subsets of equal size. That's also important to point out. Because as you remember, there is a conservation of degree along the strand in any Nicholas algebra. So if you input here size m and size n here, then output, so along this strand, this size is preserved. Likewise here. So this is the conservation of degree along the strand. And this corresponds to equalizing these two sizes. Okay, now I turn to the R matrix constructed by using the automorphism. And here we have to pick an automorphism, and there is a natural one, just by we scale each basis element by t to the power the size of the set, where t is non-zero parameter, which new parameter. So along with p, we have a new parameter t. And so we had a formula. We apply this formula, and then by using the Moy calculus, we arrive at this Moy diagrammatic formula. So you see, it looks quite similar to the braiding. We had even the same coefficient, but the difference is that now the degree is not preserved along the strands. So you see here I, which I mean you put here n, and on the output you have I, and I should be less than n. So you see that yeah, but okay, and this is the Moy formula, and then so the dependence on t is concentrated in just in this front factor. So you see that the t enters here, but elsewhere there is no t. This is just Moy diagram. And we can go further. We can calculate in explicit terms the matrix coefficients. But this time, so I use the same notation for prime sets and so on subsets. But the difference is that the summation now runs over all subsets where this beta coefficient is non-zero. Namely, this G subset, size of G subset should be bounded by the size of the H subset. Still, so the E prime, F prime are obtained from E and prime by exchanging their subsets, G and H. And then the coefficients, so we have here some supersymmetric like sign in front, and then times this R coefficient, which is essentially beta. But, so remember, beta does not depend on t at all, and all t dependence is in the front through this p Pochhammer symbol and power of t. And just remark that the power of t is positive here and everywhere, actually, because of the inequality between the sizes. And yes.
Just from the previous slide, I don't know if the question makes sense, but what is happening if p is 1?
If p is 1, nothing wrong.
No, with this deformation matrix, because so could
Yeah, so the braiding becomes just the supersymmetric symmetry.
yes, the usual in this one.
Yes, and here p. Yeah, when p is 1, so it is the delta, Kronecker delta of ni, because the Pochhammer product can be non-zero only if there is no product.
Oh, okay.
Wait a moment. No, what I'm saying. No, it becomes a 1 minus t power n minus I. No, I'm wrong. So if Pochhammer becomes a power, right? X. xp, no, 1. N is 1 minus x power n. It doesn't vanish. So, so this becomes 1 minus t power n minus I. this is one. No, this is Ti. And that's it. But here will be not quite permutation because now this I and N generally are different.
So you have the same non-trivial structure. Yeah. Okay. Thank you.
No, it doesn't function. Okay, so here is the further perspectives. So I don't know why it is. Sorry, I lost the full screen. Yes. As I said, the R-matrix we constructed is rigid, which means that there is a not invariant behind it. What is this as a not invariant? Well, conjecturally, it is a Links-Gould. I mean, you fix first the dimension of the input vector space by finite value, n, capital N. And then the conjecture is that it is a Links-Gould invariant associated with the quantum group UQGL n/1. Most studied Links-Gould invariant is the case when capital N is equal to 2. N equal 1 is less interesting because P doesn't interfere into the structure of the exterior algebra. It stays undeformed. There is no enough space to put P in. But so in a sense it corresponds to P equal 1, right? If P is absent, we can equally think that it is 1. But even for n equal 1, the not invariant coming out from this raw matrix is non-trivial. It is Alexander polynomial. But for n equal 2 and higher, so P interferes, so the not invariant is a two-variable polynomial invariant. And for some reason, so the Links-Gould invariant is not studied, and it is not as known as Jones or color-Jones polynomials. And the main reason, I think, is the Skene relation, because people like somehow Skene algebra, and but for Links-Gould, but for Links-Gould also Skene algebra exists, but it is incomparably more complicated. It involves not only a braid group in 2 strands, it involves braid group in 3 strands, and it involves also braid group in 4 strands. And the relation in the braid group of 4 strands contains 179 terms in the linear coefficient. Okay, so anyway, Links-Gould invariant is a remarkable invariant in my mind because there are colored versions of it, which are organized linearly like colored Jones polynomial, but with step 4, which means that n-colored Links-Gould R-matrix lives in 4 times n-dimensional vector space. So the Links-Gould itself is 4-dimensional, and the next 2-colored Links-Gould is 8-dimensional. And I don't know if Dror mentioned in his lecture about the V2 invariant, which is now, due to works of Stavros with his collaborator, by now it is confirmed that the 2-colored Links-Gould detects the genus up to all 18 crossing knots, with no exception. And 19 crossing diagrams are underway. Sorry, what happened?
Yes.
Yes, so. Okay, so I.
questions?
So usually, is it true that Links Gould comes from the Rashid-Deacon-Derive construction for these
Yeah,
algebras?
any invariant comes from Rashid-Deacon-Derive.
Okay.
Here the message is that we have just some complementary approach to this thing.
So can you go back a slide, please? So here Links Gould has two variables. There's P and there's T.
Yes.
So I think of P as something like the Q variable.
Yes,
in the color
it's the Q, yeah.
So what is the role of T here?
T comes in the traditional approach it serves a continuous index for representation. So representations come in a family.
So it's something like the color of the Jones polynomial?
Yes.
Okay, but this is just all packaged into one polynomial here. Okay, great.
But there is dimension also.
Sorry?
There is also dimension.
Yes, yeah.
So you have a dimension and this T. So these two together play the role of a color.
And the dimension is not n. N is the rank here.
No, not here. Not here. But there is a color Links Gould which has nothing to do with this one. But there is also n,
Okay.
like in color.
Great, thanks.
Yes.
So my question is, so U invariants strictly just reproduce what Rashid-Deacon-Derive did, or they do something new? So for example,
No, they don't do anything new. Don't expect. I mean.
But for example, there is a
standard
way
approach,
to integrate this automorphism also in
Yeah,
Rashid-Deacon-Derive.
yeah, but automorphism is something which, as I mentioned, replaces a representation, because we don't have representation here, but we have automorphism. And sometimes, if our algebra is infinite dimensional, we have to choose it carefully to be able to cut out a finite dimensional subspace.
But you have the word conjecturally. It's conjecturally Links Gould.
Yeah, it's conjecturally because we checked it just for n equal 2, 3, 4 for few simple knots, but not more, and compare it with the result of David of 2001.
So potentially it could be different.
Potentially it could be different, but practically it will not be different. I don't
Take n equals 1. Now if you get the Alexander polynomial, if you take n equals 1,
n equal 1 is Alexander polynomial.
for sure? No?
For sure.
Okay, good.
And what's the obstruction for proving that it's the same?
You should relate the algebra, this braided Hopf algebra to you have to bosonize. You will end up with the Borel subalgebra of UQ GLN1. I suspect.
You didn't know.
No, that's a way. That's a way you can proceed. And then you have to make a quantum double of that, and then relate choice of representation of the quantum double to T.
But that seems not light at all, right? It's a
It is a work, right, to be done. So, but you see, the advantage of this approach we are suggesting is that it is very economical. You have you get rid of the Cartan subalgebra completely, all the role of the Cartan subalgebra is transferred to braiding. Of course, you have to deal with braiding. It is complicated, and that's the price you pay.
and computationally, how does it compare with Links Gould? Is it faster, slower?
No, it's the same size. It's the same size. R-Matrix living on dimension 4. No, we don't gain anything in that respect. But the known R-Matrix was Links Gould was containing 26 non-zero matrix coefficients.
This is for one specific dimension or one.
Yeah, for lowest. And likewise, we get also 26 here. But in the work with Stavros, we obtained it from rank 2 diagonal type Nichols algebra. And there we got it with 25. And they are not conjugate to each other. So that's a difficulty. We couldn't prove easily the equality between two invariants. And that was done only through the complicated skein theory for the Links-Gould invariant. So that
It was done.
it was done.
In
Yeah.
special cases. So it's,
Oh,
it's
oh,
low
skein
gain.
theory. Skein theory.
Links-Gould, I mean the case n equal 2 here.
Yeah, okay. But by the way, comment, if it's not conjugate, you should test it on virtual nodes and likely it will be different. And that will kind of prove that you don't have a soft proof.
I see. Okay, I didn't know about this.
Okay.
Yep, I remember you also have some invariance which is defined using the signature of some Seifert matrix.
Yes?
Does that invariance also fit this format?
No, it is, the origin of that was a so-called IRF type R-matrix, where the variables live in the regions of the diagram. Yeah, we work with Roland on that.
It's not fit into this format.
No.
Yeah, so in your braided Hopf algebra construction, so do you know what happens if you replace your braiding you have on your vector space by its inverse? So can you compare the knot invariant you get from two constructions?
Mirror images would be.
So it's, yeah, of course, yeah, okay.
Roughly P should be inverted, I would say. But maybe not quite. But somehow in this formalism, so P never gets into negative power. That's interesting fact. When no negative gradient.
The axiom, so just to, the axiom of the braided algebra, the bi-algebra axiom involves the braiding.
Yeah.
So in the moment in which you change the braiding with its inverse, in order to get a braided algebra, you should change also either the product or the coproduct. So it's not.
Yeah, everything gets changed.
So, yeah.
And so your construction from n equals 2, does it coincide with the one from the diagonal braiding? Because this is a different braiding.
No. As I said, it contains like usual Links-Gould R-matrix, 26 coefficients here,
So it's
but
I see.
25 when from diagonal.
So it's really different. So do you expect to get these things from another diagonal one as well in higher n?
A good question. I don't know. Maybe so. Practice shows that sometimes they even are not conjugate, even though they produce same invariants.
Right.
So you see the transformation route is pretty long. The Bosonization, doubling,
Yes.
and so on.
Thanks. More questions? Well, let's thank the speaker again.